Assalamualaikum warahmatullahi wabarakatuh and good evening to our Dr. AKM Zakir Hussain. Today we are presenting about the RF and microwave to the assignment project. This is my group members is the Saidatun Nadira binti Muhammad Salihuddin, Muhammad Tariq bin Budi di Johan, and I, Ahmad Fakhruddin bin Tami Sulaiman. Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Fakhruddin bin Tami Sulaiman. My metric number is B12241045. Good afternoon to our respected lecturer Dr. AKM Zakir Hussain and everyone. Today, our group will be presenting of RF and microwave technique assignment project. As the state in the introduction, microwave filter are important component in RF and telecommunication system because they are allow desired frequency to pass while rejecting the unweighted signal. In the project, we focus on design both of the low pass filter and the band pass filter based on the Butterworth response. Finally, the entire design was implemented and analyzed using the Advanced Design System or ADS software.
Hi, my name is Muhammad Tariq bin Rudi Johan. My matrix number is B12241057. For the theory, a low-pass filter allows frequency below the cut-off frequency to pass while alternating higher frequency. In our project, the cut-off frequency is 3.5 GHz. A band-pass filter allows only a specific range of frequency to pass. The design band-pass filter has a center frequency of 3.5 GHz and a bandwidth of 350 GHz. We selected a Butterworth response because it provides a maximally flat passband characteristic without ripples, resulting in a stable signal transmission.
My name is Saidatul Nadira. I will explain the realization of design process of the project. First, we designed a 5-order Butterworth low-pass filter based on the given specifications, which are a cut-off frequency of 3.5 GHz, attenuation of 40 dB at 10.5 GHz, and a characteristic impedance of 50 ohms. Using the Butterworth approximation, the filter order was determined as n equals to 5. From the Butterworth prototype table, the normalized element values G1 to G5 were obtained and converted into actual capacitor and inductor values. The resulting circuit was implemented using a pi combination topology. After obtaining the lump element low-pass filter, Raychard's transformation was applied. This transformation converts lump inductors and capacitors into transmission line stubs. The purpose of this process is to make the filter suitable for microwave frequency applications where conventional lump components become impractical due to parasitic effects and radiation losses. Next, Kuroda's identities were applied to improve the physical realizability of the filter. This technique converts difficult to implement series stubs into practical shunt stubs and helps archive suitable characteristic impedance values for microwave circuit implementation. After applying Kuroda's identities, the normalized impedance values were converted into practical impedance values reference to the standard 50 ohm system. The obtained characteristic impedance were then used to construct the distributed filter structure in ADS. Finally, the low-pass prototype was transformed into a 5-order Butterworth bandpass filter. The design specifications included a center frequency of 3.5 GHz and a bandwidth of 350 MHz. Using the low-pass to bandpass transformation equations, the required inductance and capacitance values were calculated and implemented in ADS for simulation.
Okay, next, let's look at the simulation result for our lump element low-pass filter design in ADS. As shown by the S parameter plot on the right, the filter successfully achieved our target cutoff frequency at 3.5 GHz. At the marker M1, the insertion loss is exactly negative 3.01 dB, which perfectly aligns with the theoretical Butterworth response. Furthermore, at the 10.5 GHz rejection point, marked at by M2, the attenuation drops to negative 47.7 dB. This comfortably exceeds our initial 40 dB specification, proving that the design delivered excellent high performance filtering. Now, moving on to distribute limitation of our low-pass filter using microstrip lines. Initially, before tuning, the response deviated from our theoretical design due distribute effect, causing a slight shift in the cutoff frequency. To optimize this, we perform tuning. As shown in the after tuning plot, the frequency response improved drastic. We successfully restored the sharp butterworth characteristic and achieve significant better impedance matching.
Alright, moving to the bandpass lump. For the bandpass lump, you can see at the left diagram is the circuit diagram. For this circuit diagram, we use the lump element, meaning the discrete inductor and the capacitor. For the structure is the combination of the series LC network SLC1, SLC2 and the parallel shunt LC network PLC1 and PLC2 and the PLC3. Why the series element block the unweighted frequency while the shunt element bypass them to the ground to form the bandpass response. For the termination and simulation, connect between the two 50 omega port, the term 1 and the term 2 for the standard RF impedance matching. Simulate using the S parameter controller from the 1 GHz to the 6 GHz. Okay, move to the right diagram. The right diagram is the result of the graph. Okay, for the center frequency, successfully achieve the target of the 3.5 GHz. Refer to mark at the M2. Initial loss. For the initial loss, only have the 0.035 dB at the center frequency. This indicate the very low signal attenuation, meaning the loss is the pass band is the minimum. For the bandwidth is the approximately 350 MHz, span from the 3.33 GHz as the M1 to the 3.68 GHz for the M3, which is the 3 dB cutoff point. For the return loss, achieve the 20.9 dB. This is confirm the good impedance matching between the source and load, meaning the minimal signal reflection.
The simulation results demonstrate that the insertion loss method is effective for microwave filter synthesis. The use of Richards transformation and Kuroda's identity successfully convert the lump element design into a distributed element structure suitable for microwave applications. Overall, both the low-pass and band-pass filter satisfied the design specifications and show performance that closely match the theoretical Butterworth response. Therefore, the objective of this project were successfully achieved. Thank you.